everyone, and welcome to today's webinar. Seeing is Believing, the power of AI-trained digital imaging in microbiology, integrating BD Kiestra imaging applications into microbiology workflows. I am Kaylee Bach of LabRoots, and I'll be your moderator for today's event. Today's educational web seminar is presented by LabRoots and brought to you by BD. To learn more, visit bd.com. We encourage you to participate today by submitting any questions you may have during the presentation. To do so, simply type them into the Ask a Question box and click Submit. We'll answer as many questions as we have time for at the end of the presentation. You may also submit any technical issues here as well if you have trouble seeing or hearing the presentation. And with that, I'd now like to welcome Jane Fowler, Lab Automation Specialist for BD Canada. Jane, I'll pass it over to you to get us started.
Thank you. Hello, everyone, and welcome to this BD webinar on the power of AI-trained digital imaging in microbiology. My name is Jane Fowler, and I'm a lab automation specialist for BD Canada. We are excited to have everyone here to discuss the space of digital imaging and the benefits it can bring to microbiology labs. Today, we have Dr. Christie Vermeiren presenting on the experience with integrating BD Kiestra imaging applications into microbiology workflows. Dr. Vermeiren is the Deputy Medical Director and Clinical Microbiologist at Shared Hospital Lab at Sunnybrook Health Sciences Centre in Toronto. She is a Fellow of the Canadian College of Microbiologists and holds an academic appointment with the University of Toronto in the Department of Lab Medicine and Pathobiology. Dr. Vermeiren completed a postdoctoral fellowship in medical and public health microbiology at the University of Rochester School of Medicine and Dentistry, and earned a PhD in microbiology and immunology from the University of Western Ontario. In addition, Dr. Vermeiren is past president of the Canadian College of Microbiologists, a certified technical assessor for the Accreditation Canada Diagnostics, Vice Chair of the Institute for Quality Management and Healthcare Scientific Committee for Bacteriology and Parasitology, and co-chair of the Ontario COVID Genomics Work Quality Committee. She is actively involved in research focused on evaluating diagnostic testing strategies for the purpose of improving patient management and lab workflow, and participates in both local and national collaborative studies. It has been such a privilege to work with Dr. Vermeiren and the entire SHL team as they have transitioned from a manual traditional micro lab to their fully automated lab at Sunnybrook. It hasn't been an easy road through 2 moves and a number of other challenges that will be detailed today. As a microbiologist and mom of 3, Dr. Vermeiren wears many hats, including a construction hat. When their new lab was filled up with molecular testing equipment for COVID testing, Dr. Vermeiren quickly designed and built a new lab space to accommodate their automation in what must be record time for a hospital construction project. We are so happy to introduce you to Dr. Christie Vermeiren today.
So thank you for the introduction and welcome everyone today. I'm pleased to share with you my lab's experience integrating BD Kiestra into our bacteriology lab and our use of AI imaging applications. So I will start today with some background about my lab and focus on some of the early impacts automation has made on quality and efficiency and our validation of artificial intelligence. The cartoon on the left is one of my favorites from the mislabeled specimen. I feel that it really highlights the journey between sample collection and results and the many challenges or pricklies we face in the lab producing results, which are often underappreciated by those outside the lab. Today, I will focus on our experience with TLA and the impacts we see easing the path to producing high quality and efficient results. I understand that there are folks from the US online today. I will obviously be talking about our Canadian experience, and some of the features we use, specifically related to AI, are not available in the US. So you'll see disclaimers added to the bottom of my slides as I talk. So shared hospital lab is exactly how it sounds, a centralized microbiology lab service shared by several hospitals in Toronto and Northern Ontario. Altogether, we serve 9 hospitals and collectively just over 2,000 inpatient beds. We provide bacteriology, mycology, as well as molecular and genomic testing for infectious disease. In bacteriology, we process about 400,000 specimens per year. Shared lab is located on the Sunnybrook Health Sciences campus, and off-site samples are delivered to the lab by courier using 3 drop-offs per day. So this slide depicts the 25-year journey of SHL. Our TLA was installed in the spring of 2022, so just shortly after we changed our LIS system to Epic and constructed a new building to house the line. At no point did we wish to have all of this change occur in the middle of a pandemic, but for a variety of reasons, it did, and we survived, and that is an entirely different talk for another day. We were very fortunate as we were able to continue operating in our former space while we transitioned onto the line. The transition was done specimen type by specimen type over the course of several months, and we were fully transitioned in August of 2022. We currently process all bacteriology specimens on the Christie TLA, and since going live, we have started servicing 3 additional hospitals in Northern Ontario, and in early 2023, started operating our bacteriology lab 24/7. And so today will be about our experience this far, accounting for the early stages of TLA implementation. So this graphic shows our bacteriology specimen breakdown. As you can see, much of our work is screening for antibiotic-resistant organisms, MRSA, VRE, and CRE. Most of our sites use universal admission screening for these specimens. This screening, along with urine culture, accounts for about 70% of our total volume, while the rest is smaller volume and typical hospital bacteriology specimens. I will start with a quick photo tour of the equipment installed in our lab and our setup to add context to some of the impacts I discussed later in the talk. So this photo was taken from the front of the lab, and as you can see, the TLA takes up almost the entire lab. We have a few workspaces along the side and space in the front for receiving and sorting specimens. We have 2 Sortera and Barcodas. The Sortera holds the various types of media required for specimen processing, and the Barcoda labels the plates before delivering them to the inoculus for planting. We have 2 inocula, one on either side of the track for planting specimen. The inoculus can operate in fully automatic mode for specimens in liquid, so that's primarily our urines and all of our swabs, and accounts for about 80% of our specimens. The specimens are placed in this blue box and then planted. For non-liquid specimens, there are integrated safety cabinets. In here, the technicians scan the specimen, the plates are delivered, labeled from the Sortera Barcoda, and the technician seeds the specimen. A magnetic bead is used for streaking the plates, and once setup is complete, the plates are sent down the proceda, or the track, to the incubators. We have 5 incubators or RITAs at the end of the line. This is where the plates are incubated and imaged. Depending on the protocol, the plates are imaged at specific time points without leaving the incubators, so there is continuous and uninterrupted incubation. We have several ergonomicas on the line. So these are integrated workbenches. As the technologists read the images, they are able to call the plates to their bench to look at the plates and perform any offline tests that may be required. And so as you can see, we have quite a few screens. One of the screens is displaying Synapsys, which is the operating system used by the line. And this is where the staff look at the plate images, select the colonies, and direct plates around the line. The middle screen is our LIS screen. And the third, which was added optionally, is used for the staff to review their procedural documents and bench aids. The remainder of our workbenches are actually located in the adjacent building in our molecular lab, and we use the thinker-doer work model. The thinkers read the plates in the other building, and the doer on the line performs the assigned tasks like offline biochemicals. This model is primarily used for the more straightforward specimens like urine and screening. For identification and AST testing, we have 6 Phoenix M50 instruments, 2 Phoenix AP for setup of those Phoenix panels. So they're way back there and they're kind of hard to see, and 2 Bruker Maldies, and they are back to back. I think you can only see one in the images. We also have an integrated Kiestra Identifa for automated colony picking and Maldi setup. The Identifa is a relatively new instrument and the one that we're asked about the most, so I'll spend a few extra minutes discussing it. The technologists reading the plate images identify colonies that need an ID performed. In this image, you can see they have highlighted 2 colony types, in orange and in blue. They then order Maldi identification on these colonies in Synapsys. The system retrieves the plate from the incubator and delivers it to the Identifa. The instrument prepares a spot on the target plate and then sends the plate back to the incubator. And this all happens automatically. There are no human interventions. Once the plate is full or a specified time increment is complete, we use 30-minute intervals in our lab. The green light on the front of the instrument turns on, signaling to the technician that it's ready to be transferred to the Bruker. Once the identification is complete and the results are automatically transferred to Synapsys and the LIS. This is easily the most beloved instrument in the lab. Before TLA, staff would have to walk over to the Maldi, add their plates to the queue, and check at the end of the shift to see if their results were ready. With Identifa, target slides are being put up every 30 minutes, which greatly improves workflow. And finally, I'm told that no Kiestra installation is complete without a NOMA to watch over the lab. So let's talk about some of the quality and efficiency impacts we have seen. At the beginning of the talk, I discussed all the prickly pears that we need to overcome in our quest for results. For us, one of the biggest that we have been dealing with for years is processing specimens that arrive at the lab with a foreign barcode label. Despite being called the shared hospital lab, our sites do not share lab information systems. SHL is on the home system of SHN, one of the original founders, and interacts with each of the other sites through bidirectional interfaces to their systems, Cerner, Sunquest, and Soft. So what this means is that 70% of the specimens that arrive in the lab have a foreign barcode. And this meant that each specimen had to be relabeled with a barcode for our LIS system before we could begin processing. When the specimens arrived, they were sorted alphabetically and then relabeled, and then we would start processing. We estimated that we were spending 6 to 8 hours of people time each day dedicated just to relabeling. And as you can imagine, from a quality and error perspective, this was a function we were very eager to eliminate. With TLA, we've been able to implement foreign barcode reading. I asked our LIS analyst for a very simple diagram of how the process works, and this is as simple as he could make it. But the takeaway here is that if you have this problem to solve, you really need to go and get your LIS folks involved, maybe buy them a coffee. But simply put, the foreign barcode is scanned on the inocula, and the barcoda delivers plates labeled with our home LIS label and sends the received in lab message. I realize this is not applicable to all labs, but if you're dealing with foreign labels, this is a significant process improvement, both for quality by reduction of errors and efficiency by automating this tedious process. So now that we've achieved essentially just loading the specimens onto the TLA on receipt, The next quality improvement impact I want to highlight is customized specimen processing protocols. Synapsys has the ability to retrieve patient demographic data from the LIS. So this includes patient location, patient age, and specimen type and source. This allows you to build customized protocols for specimen setup, incorporating these demographics. In our lab, we have just over 60 unique protocols built. And prior to TLA, the technicians were required to recall these when they read the label. So an example would be adding yeast plates if a wound is received from the level 3 NICU. But the possibilities are really endless, and they can be adapted to each lab's specific needs. Setting up protocols can also be done on the fly and used only temporarily as needed. Perhaps in an outbreak scenario, you want to add a screening plate to some specimen types or from a certain location, or perhaps automatically set up extra plates for validation or research purposes temporarily. This protocol automation means that specimens are processed accurately on receipt and ensures compliance with specialized and temporary protocols that are easily missed. It's really hard to capture specific data on this improvement, but we know that often these specialized protocols were only caught a day or two later when the technologist was reading the plate, and often requiring replanting of the specimen and adding processing time. No discussion of TLA can go without mention of optimized incubation of cultures. Without the incubators continuously opened and closed throughout the day, they maintain optimal temperature. This enhances recovery of all organisms, especially the fastidious and slow growers. In our lab, we're in the process of validating the first read of positive blood cultures to 16 hours versus the traditional 22 to 24 hours, which means we can begin processing colonies sooner and an overall reduction in the time to detection. So we're getting to the top of the hill a little bit faster. I discussed previously the ability to customize processing protocols. With TLA in the microbiology lab, we are also able to customize reading work lists through digital segregation. So traditionally, labs operate on the next up culture reading. This means that technologists work through their piles of plates in the order they came out of the incubator based broadly on specimen type. For example, if you're working on a wound culture, you may read a surface wound, then a surgical wound, and then maybe a tissue. This method of work has a high mental payload for the technologists, requiring them to constantly adjust their thinking to the specimen process and protocols. And not all specimens are equal. Some are more critical than others, and some require much more complex workups. And it is difficult in a traditional lab to prioritize these specimens. Synapsys allows for customized work list building, again with the ability to take patient demographics into account. For example, allowing segregation of specimens with offline tube media, such that when the technologist picks that work list, they're signaled that they need to find the tube. Or segregating joint fluids with extended incubation times, or segregating NICU urines into a custom list because they have special notification requirements. Again, the possibilities are really endless. The dashboard indicates what is ready to read based on type, which allows for easy prioritization of complex and critical workups. For example, if a CSF is ready, they would start that workup, and while waiting for the MALDI results, read less critical specimens like stools and throats. All in all, the ability to customize and segregate specimens into custom work lists allows for efficient and prioritized processing of critical and complex specimens. So the next impact I want to talk about is workflow optimization. So this schematic depicts our pre-TLA workflow. Each technologist is assigned a unique set of tasks based broadly on specimen type. They retrieve their plates from the incubator and start their next up reading of plates. Isolates requiring further workup are brought to the processing bench and added to the queue, and they check for results when they have completed the rest of their work and then release results. This method means that incubation and reading times are not entirely standardized. Rather, they're a function of when the technologist got to them in the pile of plates. Since implementing TLA, we have put significant efforts into workflow optimization, and it is still very much a work in progress. We are now operating on a ready-to-read model with specimens organized into 3 groups based on specimen complexity, as shown in the schematic. Technologists are notified by the dashboard what is ready to read according to the customized work lists. All specimen types are read on both the day and the evening shifts. And about 9 months ago, we introduced an overnight shift with one technologist who focuses primarily on critical and urgent results. What this means in terms of quality and efficiency is that we're reading all types on at least 2 shifts, and there is no more finishing your work for the day and then continuing the next day. If I had to comment on the biggest challenge our staff faced to this transition, it would be the concept of sharing work or allowing someone else to finish what you've started. Aside from logistics, this was also probably the management team's biggest hurdle as well. We sort of dumped all the marbles on the floor and resorted them, and we're still continuing to refine. So what have we seen this far? At this point, the data that I'm showing here, we've fully automated specimen processing and implemented these workflow customizations. The graphic shows our in-lab turnaround time pre-TLA, so in blue, and 6 months post-TLA in orange for a variety of specimen types. The staffing complement and scheduled courier drop-offs were equivalent during the 2 time points, and this was before we started our 24/7 reading of cultures. The inset shows the number of specimens for each time point, and the graph shows the percent of specimens on the y-axis completed in the time span, so in 4-hour increments on the x-axis. As you can see, for the most part, with TLA, we have shifted or improved our turnaround times. Some specimen types, like stools, which are primarily negative and not high on our priority list for processing or reading, have remained essentially the same, while we see more dramatic improvements for higher priority specimens like CSF. And as you can also see, we saw this change even with large increases in some of our specimen volumes. We were very happy with these early results. Microbiology is still subject to prescribed incubation times, so despite being able to get preliminary results out faster, we still have to wait and complete our full 48 or 72-hour incubation. So changes like this, which may appear subtle, are not easy to achieve. So now for the part that's really going to change our journey to the top of the hill, artificial intelligence. Our first journey into AI has been using this technology for reading urine cultures. As I mentioned earlier, about 20% of our total specimen volume is urine culture. Within that, about 40% are no growth, and another 25% have no significant growth or insufficient growth to signify UTI. Another 10% are mixed growth, signifying contaminated urine collection, and 25% considered positive or growth suggestive of UTI. For urine culture, we use chrome-agar orientation. It's a non-selective differential media that contains a variety of chromogens to aid in the identification of some of the common urine pathogens, as shown here on the screen. The urine culture application uses an artificial intelligence algorithm to read growth on the plates through images taken in a time series. So it captures at less than 5 hours, 10 to 14 hours, and at the end of the 18 to 24-hour incubation period. The UCA uses these images to capture 3 metrics. First, the presence of chromogenic colonies, so those that I showed on the previous slide. And secondly, it calculates the amount of growth and translates that to a CFU count, as shown in the table on the screen. And finally, it captures the purity of the growth. Pure indicates a single isolate or chromogen representing greater than 99% of growth on the plate. Predominant indicates that at least 2 colony types are present, but a single chromogen represents 90 to 90% of the growth. Mixed or complex indicates that at least 2 colony types are present and no single colony type represents more than 90% of the growth. Within the app, you're able to use the 3 metrics to set up categorization or digital segregation. In our case, we're using no growth, no significant growth, and 2 growth or positive categories, 10 to 100 and greater than 100 times 10 to the 6 CFU per mil. We classify positive growth as pure or predominant of each of the chromogens or as complex. Using these UCA data points for digital segregation categories, we have set up customized work lists in Synapses. As you can see here, we have pure predominant E. coli, pure and predominant Enterococcus, complex, and so on. You're able to build what you like. We have also programmed Synapses to exclude urines that require specialized workup. This includes cystoscopy or invasively collected urines, and this is because we work up all colony types regardless of quantity and incubate for 48 hours from this source. We also exclude NICU and labor and delivery urines, and this is because we screen those for any amount of group B strep. All of these urines fall into an exclusion work list, so the technologist has signaled that these are special workup urines. And in Canada, we're able to apply auto-release of results from the UCA. I will discuss our validation over the next few slides. Included in the validation was just over 25,000 sequential, non-invasively collected urines that we used the UCA to screen. All urines were read by both the technologist, referred to here as manual review, and the UCA app, and discrepant results were reviewed during the data analysis portion of the validation. Our objective was to validate the auto-release of a final result for both no growth and no significant growth categories, and a preliminary result for pure or predominant E. coli. The urines were segregated into work lists, as I just described, and categorized for data analysis as shown here. All of the pure or predominant non-E. coli growth, or all the other chromogens, were lumped into the category PPRR, or pure and predominant requiring review. And E. coli is lumped into PPEC, so pure and predominant E. coli. And the results were classified as shown on the left. Complete agreement indicates that the technologist and the UCA agreed on classification. Tolerable discrepant, the UCA and manual review did not agree, but an incorrect result would not have been auto-released. An intolerable discrepant, an incorrect result would have been auto-released. This table shows our results. We found excellent agreement between UCA and technologist review for all categories. The results lumped into tolerable discrepant were primarily specimens with a growth score at or near the transition between categories. And when we went back and reviewed these images, we noted the urines that fell into this category were actually more accurately called by the UCA. For example, the UCA counted 90 colonies and considered accurately as no significant growth, while the technologist decided to work up because there appeared to be over 100 colonies, or vice versa. There were, however, no significant cases of under or overcalling by the app. Intolerable was found in the no significant growth category and represents 6 cases of very light, hazy Aerococcus urinae growth It was considered significant by the technologists, but classified as no significant growth by UCA. I've shown a picture here. You can see that it's very, very hard to see the growth. In the study period, UCA correctly identified growth of 18 other Aerococcus urinae positive urines. So it's not an issue with detection of the organism, rather that it started growing so late that it was not detected. We also noted that since TLA, we are seeing more Aerococcus in the urine. And this is most likely related to improved incubation conditions, and that these were most likely routinely missed before. After consultation with stakeholders and more review, we've decided to turn on auto release of no growth and no significant growth urines. And during the process of working through LIS logistics to turn on automatic calling of E. coli, so that pure E. coli will auto release a preliminary report and will automatically reflex the plate to the Phoenix for susceptibility testing. For predominant E. coli, a preliminary result is released and segregated into a work list for the technologist to select colonies for the Phoenix. And this is because our technicians perform the setup, and selecting colonies is outside of their scope of practice. So now our workflow looks like this, with AI auto-releasing results and digitally segregating work into smart buckets of work. Shown here are turnaround time graphs for final results set up at the same as shown previously with TLA, pre-TLA, in blue, TLA without UCA app in orange, and in gray with the UCA digitally segregating urines and auto-releasing. I should point out that prior to our installation of Kistra, we used a standalone WASP for automated specimen processing of urines. So automating did not have a huge impact on our workflow. I have separated urines with growth, including the mixed and complex, and on the left, no growth and no significant growth urines. So again, what we see is further improvement or shifting of the turnaround time in both categories, with slight increases in specimen volumes shown on the inset. Again, we're happy with these results. If we look at the breakdown of our urines, with UCA turned on for auto-release, about 70% of our urine cultures are resulted with the only hands-on time being racking the specimens into the inocula. E. coli accounts for about 40% of our positive growth. And again, we are using AI to auto-release a preliminary result. And this is happening 24/7, even when we're not prioritizing reading these cultures overnight. So as I mentioned at the beginning of my talk, SHL processes about 75,000 MRSA surveillance screens per year. And over the next few slides, I will review our validation of the Kistra MRSA application for AI reading of Chromagar MRSA2 plates. Again, this is a selective and differential media with MRSA growing a mauve color. This validation was set up very similar to that of the UCA, with both the AI reading the plates and manual technologist review. We included 2,415 sequential MRSA surveillance swabs. In the study period, we had 42 positive swabs, of which 41 were accurately classified by the application. I am showing the plate image of the single false negative on the screen. And as you can see, if you look very closely, there is one mauve colored colony that was missed. We also saw 174 specimens incorrectly categorized as positive by the application. I have a few examples of plates on the screen. You can see that there are indeed mauve-colored colonies or inoculum effect on these plates. This misclassification is what I would consider related to the selectivity or differentiation of the agar, rather than the algorithm, as there is indeed breakthrough mauve-colored growth. This is growth that even a technologist manually reviewing the plates would need to rule out. So overall, our positive predictive value was 19%, and our negative predictive value was 99.9. So it works great for telling us no MRSA, but not quite as good for calling positive MRSA. So this graphic shows the breakdown of our MRSA screens using the data I just showed for the validation. So even though the positive predictive value is low, the impact on workload is quite significant. 91% of specimens can be auto-verified or digitally segregated as negative. What this means for us is that the only hands-on time for swabs ordered for just MRSA screen is racking them into the inoculant. In our lab, however, the majority of MRSA swabs arrive with multiple screening orders for other ARO organisms, and this prevents us from fully utilizing the auto-release function because we have to also result the other tests under the same order. We are, however, working closely with BD and their development team to create AI applications for VRE and CPE screening using chromogenic plates, which will greatly expand utilization of AI. Nonetheless, we do digitally segregate to lump all of the negatives into a work list and then batch report, which is a significant workflow improvement. We work on the predicted positives first and then move on to batch screen and release our negatives. So this graph shows the number of cultures read by AI in the lab over time. And as you can see, we are currently reading just over 15,000 plates by AI per month. Looking forward at the possibilities for AI in bacteriology, we are working closely with BD on the development of apps for other screening specimens on chromogenic plates. I hope that in the next few years, we will realize AI reading of most or all of our chromogenic media, and which would account for about 70% of our total specimens. And if you look within this 70%, almost 90% are negative, meaning with auto release of negatives, we will have removed a significant portion of work. As for the rest of the non-chromogenic culture workups, the potential for AI to simply read all plate types for growth, no growth, will have a significant impact. In the second pie chart, we see that only 46% of these cultures had pathogens reported, while half were considered no growth. This is likely an overestimate since rest cultures with non-pathogens, for example, are lumped into this category. But nonetheless, as AI reading of plates advances, I think we will see significant change, again, in the bacteriology workload. So now to finish my talk, I'm going to talk about a few unexpected extras that we realized. So the first is validating new plates, which has become much simpler. We are able to build customized protocols to have the evaluation plate automatically set up and imaged, so there really is effortless compliance. The technologists read both plates together, side by side, and record the results. At the end of the study period, we're able to pull the two data sets from Synapsis and compare. No more clipboards to try and track all these results. We're also able to go back and review images as needed. Next is performance analytics. In essentially real time, we're able to monitor our occupancy rate as well as the time range for specimens set up and when specimens are ready to read. And this really helps us make staffing and workflow decisions. Another benefit is retrospective review of images. In this example, the resident was calling to inquire about yeast present in a contaminated urine from a patient presenting with cystitis. Traditionally, we would need to find the urine specimen, if it's still around, and replant and have the answer ready in a few days. But today we're able to recall the images from synapses and review the plate to see if yeast was present, which in this case it's not, and have the answer back within the hour. So in summary, what we have realized this far in our automation journey is that TLA has brought many important improvements to laboratory operations in terms of both quality and efficiency. We see specimens processed correctly and efficiently on arrival in the lab. Through enhanced automation like Identify, digital segregation, and AI, we have been able to adapt our workflow such that we are able to prioritize work to focus on what is important for efficient release of results. So that concludes my talk. I would like to take a moment just to thank the entire SHL team for all of their work over the past several years, getting us to the point where we're able to share our experiences. There were definitely lots of challenges along the way, but they have been extraordinarily resilient, and I appreciate everyone's hard work. And thank you for listening, and I'm happy to answer any questions that the audience may have.
All right. Well, thank you so much, Dr. Vermeiren, for your informative presentation. We will now start the live Q&A portion of the webinar. So if you have a question that you'd like to ask, please do so now. Just click on the Ask a Question box located on the far left of your screen, and we'll answer as many of your questions as we have time for. All right, so let's get started. We've already got some questions coming in here. So this first question asks, how did you approach your validation of the imaging applications in regards to confirming the accuracy of the AI? Christie, one moment. I think you're still muted here. Let's make sure. Here we go.
Okay, sorry.
No problem.
So our approach was very much to turn the application on and then just let the technologists work as they normally do. And so we let that happen for the urine application. It was for a couple of months. And then at the end, what we did was we pulled all the data out of the system. So we pulled the result that they released, and then we pulled data from Synapsys and we merged it together and started analyzing. So that's very much how we got to the data that I presented today. And we asked questions. The first was, can we auto-release no growth? Can we auto-release no significant growth? How accurate is it at calling Enterococcus pure and predominant? And then from that data set is how we decided to set up our buckets of work and work lists going forward. So you can turn it on, and basically all it's doing is making its calls in the background and just allow your technologists to continue working. And at the end, kind of put your data together and analyze and decide what you're comfortable with having done on the Synapsys workfront.
Great, thank you. All right, next question here. We saw you have the Identify system for identification. Other than what you mentioned today, how has that system improved your lab's efficiency, and how will it continue to in the future?
Yeah, so I mentioned in my talk that the lab staff love the Identify. It's sort of akin to when we introduced MALDI. That instrument was brought live, and we were immediately dependent on it, and everybody loved it. We have it set up to basically signal that a slide is ready every 30 minutes. So that's greatly improved. Before everybody would just order their MALDIs, and we had a shift, I think, that worked 10 to 6. So there was just this 8-hour period where they would sit and fill slides and get those IDs out. They were often done at the very end of shift, or sometimes not ready until they came back until the next day. So having a multi-slide being put up every 30 minutes means they send things to the multi and it comes back usually within the hour, and they know to check, or they're signaled to check for those results. In terms of going forward, as I was talking about the MRSA application, I mentioned that for pure E. coli, for the urine application for pure E. coli, we actually have the system set to automatically reflex the order to go to the bench to get a Phoenix set up. So I think what will happen as we get to a point with AI reading growth and no growth, and if it's reading pure growth of something, what will happen is that you'll be able to set up your Identifa to actually reflex, or set up your system to automatically reflex to the Identifa, so that basically the AI is reading the plate, it identifies that something's pure, and it will send that to Identifa and get an ID. And so then the technologist will be kind of signaled, perhaps it's happening overnight when they're not there, or just signaled that the ID is ready. So it's cutting out all of that work.
Great, thank you. All right, next question here asks, can you discuss your thinker-doer model and how you decide who does the thinking and who does the doing?
Yeah, so our thinker-doer model is just, it's very much, we go by experience and who's trained on what. That's how we decide who's thinking and doing. And by no means do we have our staff dedicated into thinkers and doers. They all sort of rotate through both positions, because I think it's important that everybody knows what to do. It's dictated very much by training levels. And what happens is they are reading screening plates and urine plates in the other building, and the person sitting on the line in the ergonomica just will have plates coming to them. They scan it and they see that, oh, well, this is a urine and they want a catalase set up here, or this is something that I've actually ordered ID on. It's already gone to the Identifa, and from the Identifa it goes to this doer's bench, and they need maybe they need a purity plate or something set up. So it's very much just a work in progress, and it really is changing all the time. I hope that answers the question.
Yes, absolutely. All right. We've got some great questions still coming in here. And this next one asks, let's see. All right, this next one here asks, how do you incorporate gram stain information with plate findings?
So the gram stain information, I showed the picture of the ergonomica. Even our offline benches have 3 screens. So the gram stain is, the results of that is recorded in the LIS. So they can see their plates and their images, and the information that's in Synapsys that they're recording there is also transferring into the LIS. So as they're reading their plate, they can see those gram stain results.
Great, thank you. All right, we've got time for a few more questions here. So this next one asks, you mentioned cultures may be available earlier to read, i.e. 16 hours. The Phoenix panel requires 18 to 24-hour growth. Are you validating sensitivities performed with 16-hour growth versus the recommended growth time?
So we have been doing validation of that 16 hours ever since we started. And prior to the key strat, we actually had validated using earlier growth on our panels. So that was validated well in advance. And what we're validating on the line, and that was validated years ago actually already. What we're validating on the line is that the 16-hour image and the 24-hour image, that we're getting the same set of information. So we have somebody we're working off of the 24-hour plate and then validating that the 16-hour image is equivalent to that 24-hour image.
Great, thank you. All right, next question. Do you feel the breakthrough on the MRSA media that was from, do you feel the breakthrough on the MRSA media that was being in the better conditions? And did you have data pre-implementation with this same breakthrough?
Yeah, so that has always been. So the chromogenic agar, we know that there is breakthrough growth. It's well known. If you look, an experienced technologist that has read hundreds and hundreds of these can tell by the color of mauve whether it's Staph aureus or another organism. So it's a function of the plate, not so much the algorithm. And so I think that if the plate could inhibit all mauve growth except for Staph aureus, then the algorithm would perform much better.
Great, thank you. And we did get a question in here in regards to this presentation being recorded, and it is, and this presentation will be available for on-demand viewing after the live broadcast here. So we've got time for a few more questions before we go. I know we're getting close to time here, but this next one asks, what are your best practices for implementing total lab automation in your lab, and how did you involve your staff?
So for implementation, we had the luxury of having access to our previous space. So we were really relocating to the new building. And the staff were very involved because we had to run 2 different labs. So at the beginning or on the onset, we had key user training. So the staff actually amongst themselves elected technicians and technologists to become key users on the line. And those key users were the people that started with the first steps in validating or the transition. So we validated the line, we validated each piece of instrument, and then we started moving specimens onto the line. We started with urine specimens because it was high volume, it's relatively simple work, and it really gave the ability for those key users to get a feel for working on the line and become experts on it. And then after that, we moved stools over because they're a little bit complicated. They have some offline tube incubations, etc., but they're not high consequence. So nobody really calls looking for their stool culture results, etc. So we moved something complicated over onto the line just to get a feel for how we were going to handle those types of specimens. And so those are our key users really getting a feel for the line. And then we left those 2 specimen types on and got more people familiar. And then once that portion was done, we started moving specimen types over one by one. So the whole process, we spent about 2.5, 3 months moving everything over to the line.
Great. Thank you, Dr. Vermeiren. All right, next question here asks, do you report preliminary AI results or wait for confirmatory, considering a confirmatory test like MALDI can be resulted in just a few hours?
So we report for negatives, we report a final. For positives, we report a preliminary, and then we do the confirmatory tests. So, or the AST testing. But we do put the result in. We say preliminary E. coli. For the Staph aureus, we do some additional AST testing in the background. We don't report it, but we do it. So it also goes in as a prelim, not a final.
All right, thank you. And it looks like we have time for one more question here, so we'll wrap up after this one. This final question asks, what % of your overall cultures are on the Kiestra TLA?
So 100%. So we do all of our bacteriology on the TLA. Everything goes on the line.
Great, thank you. All right. Well, that will conclude our session for today. So I want to thank you again, Dr. Vermeiren, for your time today and your important research. We would also like to thank LabRoots and our sponsor, BD, for underwriting today's educational webcast. Before we go, I'd like to thank the audience for joining us today and for their interesting questions. Questions we did not have time for today, and those submitted during the on-demand period will be addressed by our speaker via the contact information you provided at the time of registration. This webcast can be viewed on demand, and LabRoots will alert you via email when it's available for replay. We encourage you to share that email with your colleagues who may have missed today's live event. So until next time, take care, everyone. Goodbye.